Example 3. An object starts from rest, has a constant acceleration of 3 meters per second squared for 4 seconds, and then continues at constant velocity for 2 more seconds. So it's starting from rest. It doesn't say the direction here, but we can figure it out. Because if it started from rest, it's going to have to be speeding up. And it can't be speeding up in the negative direction and have a positive acceleration. Speeding up in the negative direction would be a negative acceleration. So we can conclude it's going in the positive direction, and it says that it has a constant acceleration for 4 seconds. So 1, 2, 3, 2, 4. Then after that it has constant velocity for 2 more seconds. Okay, sketching our graphs. We know the velocity was 0 at the beginning, and for 4 seconds it had a constant acceleration, and then constant velocity for another 2 seconds. So constant acceleration for 4 seconds, and then constant velocity for 2 more seconds. So whatever velocity it had at the end of the 4 seconds, it continued at that same velocity. The position time graph then would look like starting from rest, so horizontal slope, increasing slope, and then at some point it continues with that constant slope, and that was at 4 seconds. Acceleration time graph, this is a positive acceleration, and we know actually that that acceleration is positive 3. And that goes on for 4 seconds. And then for the next 2 seconds we have an acceleration of 0 because it has constant velocity. And what else can I label on this graph? I know the slope is the acceleration, so the slope must be 3 meters per second squared for this first section. The area under here would be the displacement, and this height here would be delta v, the change in velocity, and we don't know the value of this final velocity at the 4 seconds. Okay, let's do part B. Find the velocity at the end of the 4 seconds. So since I know the slope, I probably could, and I know the time, I probably could do something with that. So slope equals acceleration, which is the rise over the run, change in velocity over the time interval. And the acceleration was 3 meters per second. And the change in velocity, we don't know, but we do know the time. And I'm actually going to expand that change in velocity. So let's rewrite this. Change in velocity is always the final value minus the initial value. So the final value would be what we're going to call VF, and the initial value was 0. So this is the same as VF minus 0 because the initial velocity was 0 over 4 seconds. So that tells me that my final velocity is 3 times 4, 12, and then meters per second over second times seconds would be meters per second. So now we can label this velocity on our graph. This would be 12, and that finishes up part B. Part C, find the displacement for the entire 6 seconds. So displacement is the area of the velocity time graph, so we need to know this whole area. The area is going to be positive because it's above the time axis, and my area is going to be the area of a triangle plus the area of a rectangle. So the area of a triangle is 1/2 base times height. The base is 4 seconds, and the height is 12 meters per second. And for the rectangle, the base is 2 seconds, and the height again is 12 meters per second. The seconds are going to cancel here, and the seconds cancel here as well. So we have units of meters and meters. And 4 divided by 2 is 2, times 12 is 24, so 24 meters plus 24 meters gives us a displacement of 48 meters. So on the graphs, the 48 meters would be this entire area. It also would be this displacement here. So if it started at the origin, it would be at positive 24 meters at the end of the 6 seconds.